Hey folks, today we're going to talk about gas laws. Specifically, we're going to be talking about conversions that have to do with gas laws. So this is going to be a lot of math, so make sure you get out your calculator and that you're ready to go. We're going to have to write some stuff down here for some laws for you to remember. Okay? All right. When we're measuring gases, we typically measure four things about them. We measure how much of it there is. That's an amount. That's a quantity. And we also have a volume and a temperature and a pressure, and we refer to them as V, T, and P respectively, which kind of makes sense, volume, temperature, and pressure. So that should be pretty clear and not a problem. All right, we're going to talk about each one. Specifically, when we talk about amount, we call it M. That's the number of moles of a gas present in a sample. Yeah, your buddy the mole down here. Anyway, we're talking about the number of moles of gas present, and you already know how to do moles to grams, and moles to molecules, and moles to liters at STP, and vice versa. So we're not going to waste any time in this podcast doing that. Right? We are going to make the assumption that you can do all that. That was a couple of units ago. You should be fine with that. Right. Volume. Volume is V. Gases fill their containers, so the volume of a gas is the volume of the container. You already know that. And we measure it in certain units. We tend to use liters, centimeters, milliliters. Sometimes we use cubic meters or cubic decimeters, which we'll talk about in a minute. Bottom line is we have a bunch of units, and we're going to work on converting between them. But you should know how to convert between them. Right? Specifically, you need to know, and you should write these down, you need to know that 1 milliliter is equal to 1 cubic centimeter. That's key. You need to know that one. So write that one down. That's something you may not have seen before. Now, you already know that 1,000 milliliters is equal to a liter. Right, because milli means thousandth, so there are 1,000 milliliters in a liter. You should know that, and you should be able to figure out that 1,000 liters is equal to a cubic meter. Now, that's not something I'm going to give you on a test. That's something that you might want to think about, or frankly, it really doesn't. It's something you should be able to figure out. Really? Sure. Let's think about this for a second. 1,000 liters equals a cubic meter. Really, do I believe that? Well, how big is 1,000 liters? How big is a liter? Well, a liter is 1 liter equals 1,000 milliliters. Okay, that's cool. So that's equal to 1,000 cubic centimeters, right? We just did that a minute ago. So that means that that's 10 centimeters times 10 centimeters. That's what cubic means, times 10 centimeters. So I have a box. It's 10 centimeters by 10 centimeters by 10 centimeters. Right? Well, how do I make up a cubic meter? Well, that would be a meter times a meter times a meter, right? That's a meter times a meter times a meter. Well, if I have something that's 10 centimeters on the side, and then I put another 10 there and another 10 there, that's 30, 40, 50, 60, 70, 80, 90, 100. That's 10 times 10 cubic centimeters, right? And I can make more boxes across here and etc. I'm not going to draw them all. That would just take forever, not to mention I'm not that good of an artist. So you've got 10 across this way. Well, remember, you're going to have 10 going that way, and then you're going to have a height of 10. So 10 times 10 times 10 is 1,000. So that's each one of these is 1 liter. So that would be 1,000 liters is equal to 1 cubic meter. So you can actually figure it out if you want to. Right? But we're not going to use that very often. We're going to have some different conversion factors that you need to know. All right, let's talk about temperature. Temperature is measured with a thermometer. We tend to measure it in a lab in degrees Celsius. Now, you can do it in Fahrenheit, but we will tend to use Celsius in a lab. Now, this is very key, and I'm going to say it, and I'm going to say it again, and you're going to forget it. But you got to do it. You must convert all your temperatures to Kelvin. We can never use Celsius for a temperature when we're doing a calculation. We must use Kelvin. All right. So you can never have a negative Kelvin temperature because Kelvin is based on absolute zero. So how do I convert between Kelvin and Celsius? That's how you do it. So you should write down those if you don't already know them. Your Celsius temperature plus 273 is going to give you Kelvin, and your Kelvin temperature minus 273 is going to give you Celsius. Right? So make sure you know that. You have to memorize that. Make sure you know that. All right. Kelvin is based on absolute zero. Absolute zero is the coldest possible temperature. You've heard about this before. And at this point, all molecular motion stops. Now remember, temperature and kinetic energy are directly related. So as your temperature goes up, the kinetic energy goes up. As your kinetic energy goes up, temperature goes up, and vice versa. They both go down together. So when all of your motion stops, you essentially have no temperature. You're as far down as you can get. So when there's no more kinetic energy in your molecules, when they completely stop, at that point your temperature hits absolute zero. And we call absolute zero 0 Kelvin, which is negative 273 degrees Celsius. All right, so we want to do some conversions here. I'll do the first couple for you, and then you can go from there. All right, let's say you have a Celsius temperature of 25 degrees. How do you get to Kelvin? Well, according to this up here, we take this number and we add 273 to it. If we add 273, we get 298 Kelvin. Right. How about your next one? How do you do your next one? Well, here you have 25 Kelvin, so if we subtract 273, we're going to get a negative Celsius temperature. And our negative Celsius temperature is going to be negative 248 degrees Celsius. You'll notice, by the way, that there's no degree symbol with Kelvin. There is a degree symbol with Celsius. That's just a convention that we use. Right? So, what I would like you to do is I'd like you to go and see if you can do the next four, and then pause the video, see if you can do them, and then we'll come back together. Okay, your first one, you're adding 273, so that's 273. Here you're subtracting 273, so that's going to be 100 degrees Celsius. If I have a negative 80 and I add 273, that's going to be 193 Kelvin. And if I take 425 and I subtract 273, I believe I get 152 degrees Celsius. All right, those are temperature conversions. You need to be able to do temperature conversions. You're going to be doing a lot of them in gas laws. All right. Now, sometimes you can do things in Fahrenheit. Now, folks, I don't expect you to memorize Fahrenheit temperatures. I don't expect you to work with Fahrenheit temperatures very often because we don't do that in the lab. However, if someone were to give you the Fahrenheit and the Celsius conversion formulas, you should be able to apply them. So there's nothing magic here. So if someone gives you a formula, you should be able to think through and apply it. And folks, it is important now that you start thinking, all right? Because all of this from now on is application. It's not a bunch of memorization. It's more application. All right. So what's 98.6 Fahrenheit in Celsius? Well, that just means I have to plug that number right in there. And if I take 98.6 and I subtract 32, and then I multiply that number by 5/9, well, I get 37 degrees Celsius. Try it. See if it happens. Take your 98.6, subtract 32, take that answer, multiply by 5, divide by 9, and you will get 37 degrees Celsius. All right, you try it. What's 23 degrees Celsius in Fahrenheit? Pause the video, see if you can do it. Okay, did you put the 23 over here? You're starting with the Celsius temperature. If you didn't, pause the video again and start again. Do your order of operations. Make sure that makes sense. Right, order of operations says you do this first. So I take 9 divided by 5, that's 1.8. I multiply by 23. And then I add, when I'm all done with that, I add 32 degrees. Right, and my answer is going to be 73.4, or if you want sig figs, 73 degrees Fahrenheit. That would be a very comfortable room temperature, wouldn't it? Right, so it wouldn't hurt you to know that body temperature is 37 Celsius. It's kind of a good number to know. And, about 23 degrees Celsius is a nice room temperature. Those are kind of good numbers to kind of keep in the back of your head somewhere. All right, pressure is the big one. And pressure is how much force does a gas exert on its container. It's pushing out. Remember what we talked about when we were talking about the balloon in the last podcast is all the gas molecules are pressing against the inside of that. They're bouncing around and they hit the inside of the container. and that's what keeps the container open, the balloon open. All right, so we have a lot of different ways that we can measure pressure. It's kind of like measuring length, right? Because you could say, well, 1 yard is equal to 3 feet, is equal to 36 inches. Right? You can do the same thing with 1 gallon is equal to 4 quarts, is equal to 8 pints, is equal to 16 cups. Right? All of these mean exactly the same amount. It doesn't matter whether I give you a gallon of milk or 16 cups of milk. I'm giving you exactly the same amount of milk. Well, the same thing is true here. These are simply conversion factors. We've got atmospheres, and we have something called torr, and that is the same as millimeters of mercury. We also have inches of mercury. You have to just convert between inches and millimeters. We also have pounds per square inch. This is something that we use a lot for measuring, for example, tire pressure. Americans use pounds per square inch a lot. We don't use it much in a lab, but certainly it is something you need to be able to convert between. We have pascals and kilopascals, which is simply dividing by 1,000. And we have something called millibars, which we don't use, but if you happen to watch the Weather Channel, they're always talking about millibars, and those happen to be hectopascals. So, we have some strange measurements that we use, that people use, and we tend to use different ones in a lab. So, what is all this about atmospheric pressure? Where does this come from? Well, it comes because we have, air has mass, and it's attracted to Earth's gravity, and it's all above us. And it's pushing down on our heads all the time. And on our bodies, we have all of this air pressure. Remember that the gas molecules are going in every direction. So when we're standing here, we have air pressure pushing on us in all directions. Now, it varies by altitude. The higher up you go, the less air pressure you have. Why? Because you've got less air pushing down on top of you. You're further up. Okay? There's less air up there. Harder to breathe. The air's not as dense. All right, so we measure atmospheric pressure by using a barometer. Now, you'll happen to notice that this is in millibars. Yeah, again, something that we don't use. And the outer ones are in inches of mercury. Again, something we don't use in the lab, but they are things that people will use when they have a barometer and when they're listening to the Weather Channel. So why do we care about pressure? Well, we care because it affects our weather, or our weather is affected by pressure. For old people, they'll say, oh, I feel it in my knees. We're getting a storm coming in. Right? Airplane altimeters. How does an airplane know how high it is? It's all based on air pressure. And 1 atmosphere is equal to 14.7 pounds per square inch. What exactly does that mean? Well, that means that at sea level, there's about 14.7 pounds pushing on every square inch of your body from air pressure. I know that's hard to believe, but really it's there. And if you talk to me in class, you talk to Mrs. Sherman in class, we can actually show you what that means. And you'll be doing a lab to demonstrate that, of how much pressure is actually pushing down on you, and that same pressure is actually pushing out from your body as well. So how does it affect your body? How does it affect the things around us? Well, if you've ever driven over Sugarloaf Mountain Road, which I do a few times a week, you'll notice your ears pop. Why is that? Well, it's because the pressure on the outside of your ears isn't as much as the pressure on the inside of your body. So it has to equalize. So your ears pop. If you go swimming and you dive down to the bottom of a 12-foot deep pool, you feel it as well in your ears. Again, the same things. That pressure has to equalize. The pressure on the inside of your body is pushing out, and it hasn't stopped. But there's less pressure pushing in. And all we did was go over Sugarloaf Mountain Road. We only went up a few hundred feet. What happens when you go up a few thousand feet, in an airplane, for example, or climbing to the top of Mount Everest? Okay. Now, when you look at the surface temperatures, here's an example of a map from a year or two ago. You'll notice that the high pressures mean it's bright, it's sunny. The high pressure pushes the water away. But look at the low pressure systems. The low pressures has all this rain near it. We've got rain near low pressures, right? Low pressure is where all the moisture is. So yes, people can feel that when they talk about their arthritis. In fact, if you have a really, really, really low pressure system, like we did with Hurricane Sandy in 2012, in the fall of 2012, you get this massive low pressure system, which has bunches of rain and wind associated with it. Right? And here are all of the gradients of the different pressures as you work away from the center. Right? Kind of cool to see that, now that you understand what it is. All right, so we need to be able to do pressure conversions. And the standard is set at sea level. And you need to stop and write these down, so pause the video and write it down. These are the ones that we expect you to know. 1 atmosphere is 760 millimeters of mercury. Millimeters of mercury and torr are exactly the same thing, so that number is the same. 1 atmosphere is 101,325 pascals, which if you divide by 1,000 are kilopascals, so these two are really closely related together. And then the ones that we tend to use a lot in America is that there's 14.70 pounds per square inch. All of these are equal to 1 atmosphere of pressure, or the approximate average pressure at sea level. Now, of course, we live in Roanoke, Virginia, so our pressure tends to be a little bit less than this. If we lived on top of a mountain, it would be even less than that still. Okay. So let us go and do some math and do some calculations. We have to be able to convert between atmospheres and torr, atmospheres and millimeters of mercury, etc. So let's go ahead and do one. These should look very, very familiar because all you're doing is using conversion factors just as you always have. So you always start with the information you're given, which is 1.67 atmospheres. And we're trying to convert between atmospheres and millimeters of mercury. So do we have a conversion factor between atmospheres and millimeters of mercury? We sure do. We notice that 1 atmosphere is 760 millimeters of mercury. So you should already have this on a sheet of paper, so I'm not going to bounce back and forth to this slide over and over. But you need to be able to go and look at your piece of paper and look at what your conversion factors are. Well, since 1 atmosphere is equal to 760 millimeters of mercury, I can put atmospheres down here because I want to be able to cancel atmospheres, and I want to be able to go to millimeters of mercury. And there's 760 millimeters of mercury in 1 atmosphere. So I've canceled my atmosphere. I'm left with millimeters of mercury. That's what I was trying to get in my problem. So if I go and I plug this into a calculator, I'm not going to waste your time doing that. That's 1269.2 millimeters of mercury. But I have to round that because of sig figs. So that becomes 1270 millimeters of mercury. And you might say, well, wait a minute. I only have 2 sig figs here. We assume that the numbers in our conversion factors are perfect numbers. So we don't worry about those. We always look at the number we're starting with. And our starting number had 3 sig figs. Our ending number has 3 sig figs. All right, how about this one? See if you can do this. Pause the video. Try it on your own. All right, we start with the information we're given, which is 167 kPa. Now we're trying to go from kilopascals to atmospheres. Kilopascals obviously has to go on the bottom. Do we have a conversion factor between kilopascals and atmospheres? We certainly do. And we can see that 1 atmosphere is 101.325 kilopascals. When I do the math and I do this division, I come up with 1.65 atmospheres. Folks, let me make a point. I'm not sitting here and looking these numbers up. I've done enough of these problems that these numbers now come easily to me. You should do enough of these problems so that you don't have to think about these numbers, that they're just on the tip of your head without even thinking about them. All right, pressure inside a container is 16.7 psi. What is the pressure in millimeters of mercury? Well, do I have a conversion factor between psi and millimeters of mercury? Well, no, I don't. So how do I get there? Well, if I look at my chart, I can see that I can go from psi's to atmospheres. And then I can go from atmospheres to millimeters of mercury. So let's do that. I'm going to go from psi's to atmospheres. And then I can go from atmospheres to millimeters of mercury. And 1 atmosphere is 14.70 psi. And 1 atmosphere is 760 millimeters of mercury. So I'm going to take the 16.7 divided by 14.7 psi, multiply by 760 millimeters of mercury, and I come up with 863 millimeters of mercury. All right, let's see if you can do one like that. All right, here we have the pressure inside a container is 16.7 psi, and what's the pressure in pascals? So pause the video, see if you can do this one. All right, this is the last one we're doing. We're starting with 16.7 psi, pounds per square inch. Pounds is force, square inch is area, so it's force per unit area. We are getting rid of PSIs, and what are we going to? Well, we can't go to pascals. But what we can do is go from PSIs to atmospheres. And from atmospheres, we can go to pascals. So let's go to atmospheres, and then from atmospheres, we can go to pascals. And 1 atmosphere is 14.70 psi, and 1 atmosphere is 101,325 pascals. When we multiply this out, we get 115,110 da 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 da. Well, again, we have to round to 3 sig figs, so this is going to be 115,000 pascals. All right, I think that'll do it. So what you need to be able to do is you need to be able to do temperature conversions between Kelvin and Celsius. You need to know that that conversion factor is 273. You need to be able to use it and know whether you're adding or subtracting. Furthermore, you need to know these pressure conversions. You need to know that an atmosphere is 760 millimeters of mercury, which is also torr. You need to know that it's 101,325 pascals, or 101.325 kilopascals. And you need to know that it's 14.70 pounds per square inch. Right? You need to know those conversion factors. If you didn't write them down, write them down now. You're going to need them. All right? If you have questions, go ahead and go do the worksheet. If you have questions, see us in class. We'll be happy to help you. Have a good day. Bye-bye.